The Kepler telescope watched and watched. For 4 years it stared at a patch of sky in Cygnus, recording the steady glow of a distant star. Then the data began to scream. The star's light plummeted, jagged and deep, vanishing like a candle snuffed in a storm. Not the smooth, predictable dip of a planet passing. This was erratic, profound, impossible. The dips were immense. Up to 22% of the star's light disappeared in moments, far deeper than any known planet could block. And the pattern, it was chaos. One dip lasting hours, another days, then weeks of normal brightness, then another sharp plunge. No rhythm, no repetition, just darkness where light should be. Worse, the star wasn't just dimming temporarily. Long-term data showed a slow, steady fade over decades. Its fundamental brightness was changing, as if something had settled permanently between it and Earth, slowly thickening like dust in a forgotten room. Citizen scientists scanning the Kepler data flagged it first. They were volunteers, not professionals, working through the noise of the telescope's endless stream. They saw anomalies the algorithms missed, a strange, irregular dance in the light curve. They pointed out the impossible to the experts, forcing a closer look. Astronomer Tabby took up the case. She published the anomaly in 2015, giving it the catalog number KIC 8,462,852. The star became known as Bayesian star to the public, though astronomers still used the technical name. The data was undeniable. Something massive, something strange, was obscuring its light. Later teams used telescopes sensitive to different colors. They observed the star as it dimmed across blue, green, and red light. The dips looked different depending on the color. Blue light dimmed more than red. This was critical. It meant the blocking material wasn't solid. It scattered light like fine dust, not a planet or a structure. Fine dust. The dimming wasn't caused by a shadow. It was caused by particles so small they scattered starlight in all directions, like smoke in a cathedral. The dust was diffusing the light, making the star appear dimmer, not blocking it entirely. A solid object would dim all colors equally. The dust's origin remains a mystery. We see the effect, but not the cause. It could be remnants from a shattered comet, its fragments drifting in a chaotic cloud, not the orderly stream of a single comet. Or it could be dust from a long-ago planetary collision, debris still swirling around the star after decades. Some scientists proposed a swarm of comets, but comet debris usually causes predictable patterns, with dips matching the comet's orbit. The dips here were too deep, too irregular, and too long-lasting. A single comet couldn't create this pattern, and multiple comets would leave a signature in the light that isn't present. Another theory suggested a shattered planet, its dust creating a permanent cloud. But planetary debris disperses quickly within years. The star's dimming has persisted for decades. The dust should have vanished long ago, leaving the star bright again. It hasn't. No single explanation fits. The dust is confirmed. The irregular pattern is real. But its source, its history, its very reason for being, these remain hidden in the data. Each new observation adds a sliver of detail, yet the full picture stays just out of reach. The key lies in the dust itself. If astronomers could determine its composition, or catch a new dust cloud passing across the star, the answer might emerge. They now monitor KIC 8,462,852 constantly, gathering light across the entire spectrum. Every faint change in the star's glow is logged, every ripple in the data analyzed. They have the tools, they have the data. They see the star dimming, the dust scattering its light. But the question of where that dust came from, the event that created it, remains a silent void in the vast, dark sky. The star blinked, the dust stayed, and the story it tells is still unfinished. What could make a star dim like this?